let's continue, and this brings us up to decision trees. And so we're going to look at decision trees in random forests. Now, there's actually an intermediate step that is reflected in the exercise bagging, and we'll talk about that at the right moment. But what we have here really, what is a decision tree? Decision trees are related to regression, but they're not parametric like that, and they do not comprehensively incorporate the relative influences of all of the predictive variables in a linear modeling type fashion. Decision trees they're a regression type approach. You could say they're quasi regression or quasi parametric, I guess. But what they do, and there are two types. There are really two types of tasks that you can perform with decision trees. You can, and they're very simply differentiated. What you're trying to do is you're trying to predict some outcome variable, just like regression, where you have you have values of a y variable, and you regress that on various x variables. And in regression, linear regression, you get these coefficients that minimize the sums of the squared errors and draw a straight line through all the points. You're kind of doing the same thing with decision trees. You're trying to predict the value of y, but y can be a factor like ANOVA. Y can be levels of a factor, in which case it's really a classification task. You're trying to predict the class that the outcome variable falls in based on the values of the numeric predictive variables. Or it can be a more like regression, where the target variable, the predicted variable, is actually numeric. And then so sometimes this technique in general is called CART, C-A-R-T, which just stands for classification and regression trees, in recognition of the fact that you have two different types of task: a classification task when the target variable is factor, and a regression task when the target variable, the predicted variable, is numeric. And there are different functions and different packages that do one or both classification and regression. And these functions in the different packages have their own unique strengths and weaknesses. So we're going to first look at an example that is used quite a bit, and we'll see it again even tonight, on the IRIS data set. And the IRIS data set is another one of those data sets that is automatically installed with the base installation. You just have to invoke it to make it visible down here so we can pop it open with the data command. And so we'll do that. And if we look at it, the IRIS data set is 150 observations of individual flowers, each of which belongs to the iris type flower, iris species, iris flower. And there are three species. There's the setosa, there's the versicolor, and virginica. And we have exactly 50 records of each one. This is a classification task. We're trying to predict the classification of each of these iris flowers. There's 150 of them, based on their observed values for the sepal length, sepal width, petal length, and petal width. So these four predictor variables are numeric. So this is a classification task. And we're going to build a decision tree. Now, a decision tree, depending on the function, this first example, okay, well, how are we going to do this? It's a good idea to look at the structure of any data set you load. Like in this case, it'd be IRIS. So if we say str is one of my favorite commands because it shows you within the data frame the name of each variable, the type, the information about the values, and we can see very easily that species is a factor and these are the levels. And so it gives you a really good quick grasp of what the variable types and ranges are in your set, it's a good idea when you use the sample. We're going to use the sample function to separate it into both test and training sets. Sample will randomly select from a set of observations either with replacement or without. Without is the default. And so what you can do with sample, in this case we're using kind of a strange syntax, but what we're trying to do is we want to separate this 150 record data set into 70% for training the tree and 30% for testing the tree. And the 70-30 protocol is used quite often in data mining. Sometimes it's less. Sometimes it's 70, 15, and 15. But you certainly don't want to test the predictive ability of your model on the same data that you trained it with, because it's going to do better. It's, when you test it on the same data that it was trained on, it's going to do better. The acid test is when you test it on a new set. So you usually hold out at least 30%, sometimes less. What sample does, this actually, let's do it. So if I'm using the sample function, it'll sample without replacement. Every row number, it'll do for 150 times. For every row in Iris, it will select either a 1 or a 2. It'll sample from the sequence 1 to 2. 70% of them will be 1s and 30% of them will be 2s. And so it's associating either a 1 or a 2 with each row just by the order in Iris. So if we look at this outputted object, we see that what it is, it's 150 1s and 2s, where whatever 70% of 150, which I guess 105 of them are 1s, and 30%, 45 are 2s. Now I don't know if I hit set seed, but if you do set seed every time you run this, you're going to get the same result. If I don't hit set seed every time I do this, it'll be different. But you can see I just made sure that I hit set seed. So calling the set seed function will ensure that your sampling between the 70 and 30% is identical each time if you want to replicate the results. And so then all we have to do is we just say, well, take the Iris data set for those rows. This is row 1, 2, 3, 4, leave out 5, include 6, 7, 8, and put them in the training data set. So this will strip out the whole record, not just the row number, but note it skips rows. It's using 105 of them in the order in which the 1s and 2s were generated. So we miss row 149, 147. And the other one, we can say, what are the row names? These are the row names for everything in Iris. So it's just selecting these numbers. And 105 of them will be in training, and whatever the other 45 will be in test. Okay, so then we do the same thing for test. And if we look at the test data set, it only has 45. So we've separated the data set randomly into 70%, 30%.